Welcome crew, these are our 8.2 notes on comparing exponential and linear functions. So first of all, we're going to talk about how to, from a set of data, right, which we have here in this table, identify whether we have a function that is linear and exponential. So I'll remind you that one thing we learned is that linear functions grow by a constant rate, whereas exponential functions grow by a constant percentage rate. Okay. So with data, the first thing you've got to be careful to look at is whether x is changing by a constant amount. So if we look at the values of x listed in this table, when x goes from 20 to 25, it increases by 5, right? As we do to go from 25 to 30, 30 to 5, and so on. And so we have a change in x that is constantly 5. So yes, our x is changing by a constant amount. The next thing we'll look at is whether y is changing by a constant amount. And if so, then we should be able to, what this statement means here, is subtract consecutive x's. So this y sub n plus 1 means a next y, minus y sub n would be its previous y. So if we were to subtract y's, right, working backwards along the way, and we always get the same number, then we have a linear function. If we don't get a constant difference between y's when x changed by a constant amount, right, then the next question is whether y is changing by a constant percentage. We find that by looking at the ratio or the quotient of consecutive y's. So we would divide a y by its previous y. If that gives us the same number, right, then we have an exponential function. So this same number that we get is a common difference, right? That difference comes from subtracting. The same number we get when we divide is called a common ratio. A ratio comes from division. Common ratio. Okay. So let's do that here with this example. So for f of x, I'm going to take my y's and I'm going to first subtract them. So to determine whether my function is linear, I'm going to take my second y, which is 45, and I'm going to subtract my first y, which is 30. So this would be my y sub n plus 1. This is my y sub n. Well, 45 minus 30 is 15. That alone isn't enough to determine that the function is linear. All differences between one y and its previous y should also be equal to 15. So from there we go on and we say, okay, does that equal what we get when we take the next y, 60, and we subtract its previous y? Right? Is 60 minus 45 equal to 15? Right? Well, yeah, it is. Well, that again isn't enough. We have to move to the next one. So is 75 minus 60 equal to 15? Right? Is 90 minus 75 equal to 15? Is 105 minus 90 equal to 15? Right? If those differences are consistently 15, and they are, then yes. Right? So f of x is linear. Let's go on now and look at g of x. So if we look at g of x, and we ask the question again, is g of x linear? Then we're going to take, right, the second y from g, which is 1200, and subtract the previous y, which is 1000. Right? Which in this case we get 200. Right? And again, that's not enough. We've got to go on. So now we're going to take the next y and subtract the previous y from that. So does that equal 1440 minus 1200? Well, 1440 minus 1200 is not 200, it's 220. And if we go beyond that, right, and take the next one, we get 1728 minus 1440, right? We get a difference now that's even bigger than 220, the difference we got from here. So we can see that there is not a common difference when we go from one y to the next, that the y values are actually growing by a greater and greater amount, not by the same amount. So the next question we ask when we determine that no, it's not linear, right? So this would be no, is it geometric? Or I'm sorry, is it exponential? Well, the way we test exponential, right, is similar in that we take our subsequent y's, our consecutive y's, and we divide them. So I'm going to start with my second y, 1200, and I'm going to divide it by its previous y, 1000. So if I take 1200 and I divide it by 1000, I get 1.2. So the question then is do I get 1.2 when I divide my next y, right, that was my 1440, by 1200, the previous y, right? And if you'll check that, you do actually get 1.2, right? If we go on and we do 1728 and divide that by 1440, we also get 1.2, and if we were to check that, yes, we get 1.2. So is it exponential? The answer is yes. So if you look at data and you're trying to determine if it's linear or exponential, look for a common difference by subtracting y's or a common ratio by dividing y's. Okay, so now once we've determined whether our function is linear or exponential, then we're ready to write an equation, which we've done for both of those, but we're going to look how to do that with kind of different information. The first thing we need to know is that the general form of a linear function is f of x equals mx plus b, right? You know that as y equals mx plus b. So very familiar equation. I want to take that to a different form though for you, right? Would you agree that mx plus b, because addition is commutative, is the same thing as b plus mx, right? And then from there, right, the letters we use are not really important, it's their meaning, right? So this b is our y-intercept, this m is our slope. So if we change b to a different letter a, and we change slope to a different letter b, then I could say f of x is equal to a plus bx. Both of these linear equations, because our x is only to the first power and only involved in multiplication and then adding a constant. We've been using our general form of an exponential function, which is f of x equals a times b to the x. Okay, the reason we change the form of linear is so that they'll be similar. We'll look at this on the next page. They both start with a, and then they both have a b. And that b is going to be related to our rate of change. All right, so once we've determined whether we have linear or exponential, we have a form that we can use, then we're going to go through this process, whether it's linear or it's exponential. Number one, we're going to select 2 points from our data set, and then we're going to write those in function notation. Right? And then we're going to write 2 equations from our 2 points, and then we're going to solve those 2 equations, which make up a system, either by linear combinations, if we have a linear function, or by dividing the 2 equations for exponential functions. I'll show you. Okay, so in our first equation for f of x, we're going to start with 2 points from our data table. So we had the point, our first point was when x is 20, y was 30, and our second point was when x was 25, y was 45, or f of x was 45. And actually, I think I'm going to skip writing these in function notation. No, I won't. All right. So this tells me f of 20 equals 30, and it tells me that f of 25 equals 45. Okay, so now I'm going to plug those into my general form for f of x, which is going to be in the form of f of x, and I'm going to use a plus bx. This would also work if you used mx plus b. Now, because in linear combinations I'm going to subtract, and I would rather subtract a smaller number from a bigger number, I'm going to take these 2 points and I'm going to flip their position. So I'm going to take this second point and I'm going to plug it in. For f of x, I'm going to plug what f of x equals, which is 45. That equals a, which I don't know. I would like to. Plus b, which again, I don't know, right? I need to know what a and b are, and I don't. But I do have a value for x because I know that f of 25 equals 45. Right? So my 25 goes there. Okay. Now I'm going to take my second equation here and I'm going to make the similar substitutions. So for f of x, I'm going to put 30. F of 20 is 30. That will equal my unknown a plus b times my x, which in this case is 20. So now for linear combinations, I want to find a and b, and I'm going to start by subtracting these 2 equations. So when I'm going to have to borrow some space here, but when I come in here and I subtract these 2 equations, I'm going to do 45 minus 30, which is 15. Then I've got a minus a, which is 0, plus b times 25, which is 25b, minus b times 20, which is 20b. And 25b minus 20b is 5b. Right, so I've eliminated a from my equation by combining these 2. I can now solve for b by dividing both sides by 5, and I get that b must equal 3. Right? That's one of the things I need to know. Now I need to know what a equals, right? And you've done this before, so you take one of your 2 equations. I'm going to take this equation because it has smaller numbers along with my value of b, and I'm going to rewrite this. So I have 30 equals a, right, which I still don't know, plus b, which I now know is 3, times 20. So that's 30 equals a plus 60, 3 times 20 is 60, which means a equals negative 30. I now know a. My objective is to get a linear function for f of x. I have what I need, and I now know that f of x equals my a, which is 30, plus my b, which is 3, times x. And I have a equation for my linear function for f of x. I left off my negative in my 30. Okay? So you've done that before. That's not really new. We just kind of used a different form for our linear equation. Right, now let's do it for g of x, which was exponential. So I'm going to have to erase this. So I've got my space. So g of x is exponential, which means that g of x is going to be of the form a times b to the x. And I'm going to start with 2 points from g of x. So I had the point 21,000, and then I had the point 25, 1,200. So that means that g of 20 equals 1,000, and g of 25 equals 1,200. I'm going to plug that information into my general function, right? To get an equation for g of x, I need to know what a is, I need to know what b is, right? Those are 2 unknowns. To find 2 unknowns, I need 2 equations. Each point is going to give me an equation. For exponential, I'm going to divide instead of subtract. But like in subtraction, I would rather divide a bigger number by a smaller number, right, than the other way around. So since my bigger number is on bottom, I'm going to switch my order here, and I'm going to plug in 25, 1200 first. So for g of x, I'm going to plug in 1200, right? G of 25 is 1200 equals my unknown a times b, and the x I'm going to use is the x from that point, which is 25. With the second point, I'm going to plug that in, and I get 1000 for g of x equals a times b raised to the x, which in this case is 20. Now, I'm going to take these two equations and I'm going to divide both sides. When I divide 1200 by 1000, I get 1.2. Seems like we've seen that number before. Equal, my a's divide out, and I'm left with b to the 25 divided by b to the 20. And when I use my properties of exponents, I subtract those exponents and I get b to the 5th. Okay, now to solve for b, we're going to raise both sides to the reciprocal of this exponent, so to the 1/5. And that gives me, come up here, that gives me that b equals 1.2 to the 1/5, okay, which is the exact value of b. If I plug that into my calculator, I get about 1.0371. So I found b, right? There's my b. I still need my a. So now I'm going to come in and I'm going to take one of my equations. I'm going to take this one along with my value of b, and I'm going to substitute my value of b. So this equation says 1000 equals a times b, and I'm actually going to use my exact value here. If you're using your calculator, you can use that from your calculator without rounding. Okay, so I'm going to take the 1.2 to the 1/5, and then we're going to raise that to the 20th. So that gives me 1000 equals a times 1.2, power to power, I multiply 1/5 by 20, and that gives me to the 4th. So a equals 1000 over my 1.2 to the 4th, which if I evaluate that on my calculator, for a I get about 482.253. So if I put those two together, right, so there's my a, I put those two together, right, so bringing this here, I get that my equation for g of x is my value of a, which is about 482.253, times my b, which is about 1.037 raised to the x. And that's my exponential function. Okay, at this point, I want you to do something for me. Okay, I want you to pause the video, and I want you to do from your worksheet 8.2, problem number 3, and you'll report those answers on your Google form. All right, welcome back. Let's continue on with these notes. Right, and let's talk about some similarities and differences between linear functions. So first of all, we've already talked about rewriting our linear functions as f of x equals a plus bx. So that's the form of our linear function we're going to use. And we have our exponential function as a times b to the x. So if we look at what they have, right, they both start with our value of a. Remember, that's our initial value. And then adding b times x means that we're going to add x number of b's. Multiplying by b to the x means we're going to multiply by x number of b's. So in linear, we have repeated sums, whereas in exponential, we have repeated multiplication. In both cases, x determines our number of repetitions, right? And in both cases, a is our y-intercept or our starting value. Okay, in a linear function, b is our constant rate of change, which is our slope. In an exponential function, b is our growth factor, right? Not our rate of change, but by how much we would multiply, right? Remember that we can find r from that. Okay, as far as the graphs go, an important thing to memorize, to identify is, right, if both our functions have the same y-intercept, even though there might be a portion of time where your linear function values are above your exponential function values, right, because exponential functions grow by more and more, whereas linear functions always grow by the same amount, exponential growth will always outpace linear growth. So if you're looking at graphs, you can know that in the end, in the long run, your values from an exponential function will always end up larger than the values of your linear function. All right, let's look at an example here. Okay, at time t equals 0, a species of turtle is released into a wetland. When t is 4, a biologist estimates there are 300 turtles in the wetland, and then 3 years later, the biologist estimates there are 450 turtles. Let p represent the size of the turtle population year t. For A, our job is to find a formula for p of t, assuming linear growth. So I need a formula for p, assuming linear growth. I then need to interpret the slope and the p-intercept of our formula in terms of the turtle population. That means I've got to talk about turtles. All right, so let's look at what we've got. First of all, let's define our variables. So based on this, we are, well, this is defined already. Let p represent the size of the turtle population, right? So p is the number of turtles. Okay. In year t, right, where at t equals 0, the species is first released. So that means t is going to be, the number of years since release. Okay, since the turtles were dropped into this wetland. Right. So what do we know? We know that when t equals 4 years, that the biologist estimates there were 300 turtles. Right? With these variables, t is our independent variable, p is our dependent variable. So in form of a point, I know that when t is 4, p is 300. Okay? It then says that 3 years later, so 3 years later would be when t is 4 plus 3 or 7, the biologist estimates there are 450 turtles. So that would be the point t, that would be the point 7, 450. Okay, so if we are going to assume linear growth, then we're going to take these points and we're going to write them in the form of a linear function. Okay? So let's see if I can move these down at all. All right, I think that'll work. So I know that my formula should be in the form of p of t equals a plus b times t. All right, remember these are t's, these are p's. So when I come in here and I make my substitution, I'm going to use my bigger numbers first, so I'm going to put these up. I get 450 equals a plus b times 7. Taking these numbers and substituting them, I get 300 equals a plus b times 4. Now I'm going to take these two and I'm going to subtract them. So when I subtract, I have 450 minus 300, right? Subtracting those, it gives me 150 equals a minus a, those are going to subtract out. I get 0, right? I'm left with b times 7, or 7b, minus 4b. So that's 3b. And if 150 equals 3b, then b equals 150 divided by 3, which is 50. So there's my b. Okay. Now I'm going to substitute, taking one of my equations. I'll take this one along with my b, and I get 300 equals a plus 50 times 4. Right? 50 times 4 is 200, so that gives me a equals 100. Putting those together then, I get my equation says that my population of turtles should be modeled by the equation 100 plus 50t. Okay. So, right, the other things we need to do is interpret. Right? And the first thing we had to interpret was the slope. When you interpret, make sure you identify the slope. So our slope is our coefficient of our variable, which is 50. And if we want to interpret that, remember linear functions grow by a constant amount. We know that the turtle population is predicted, right? A model is used for prediction, to grow by about 50 turtles each year, right? T was in years. Okay. So the other thing we were supposed to deal with is the p-intercept. So let's talk about that p-intercept. The p-intercept is our a value, that's 100. So our p-intercept is 100, that's our initial value. So it tells us that about 100 turtles were initially released into those wetlands. Okay? So that's our A. Now let's find a formula for P. We're going to do B now of T, assuming exponential growth. And we're going to interpret the parameters. The parameters are the numbers, so that would mean we're going to interpret A and B. Okay. So we're going to take our same 2 points for B. So for B, we're going to take our points 4, 300 and 7, 450. But this time, we're going to put them into the form of an exponential function, so that would be P of t equals A times B to the t. So making my substitutions here, right, again, I'm going to put the bigger numbers on top. I've got for P of t, I have 450, that's my population, equals my unknown A, times B, my time is 7 years, so there's 7. Taking my second point, I've got 300 equals A times B to the 4th. Okay, I'm going to take those two equations now, and I'm going to divide them. Okay, so when I divide them, 450 divided by 300 is 1.5. My A's will divide out, and B to the 7th divided by B to the 4th will give me B to the 3rd. To solve for B, we're going to take both sides and raise it to the reciprocal of that exponent, which gives us B equals 1.5 to the 1/3, which is about, if I put that in my calculator, 1.1447. So there's my value of B. Okay, I'm now going to come in here and I'm going to substitute. So I'm going to take my smaller equation along with my value of B, and I'm going to rewrite that as 300 equals A, which I still don't know, times my B, and I'm going to use my 1.5 to the 1/3, right? Or again, you can pick up, right, your decimal approximation from your calculator, and we're going to raise that to the fourth. So that gives me 300 equals A times 1.5. Multiplying these exponents, I get to the 4/3, and A is 300 divided by 1.5 to the 4/3. If I put that in my calculator, I get about 174.716. Okay, that gives me that my equation, P of T, is equal to my A, which is 174.716, times my B, which was about 1.1447 raised to the T. Right? So that's my exponential equation. So if I come in here and I interpret my values, my parameters were A, which was 174.716, right? And that would tell me that about, what, 175 turtles were initially released. And my B value is 1.1447. And for me to interpret that, I'm going to find my R, right? So in my linear, I talked about slope, which was a growth rate. I'd like to talk about my growth rate here. So my R is going to be my B minus 1, which if I take 1.1447 and subtract 1, I'm going to get 0.1147. So if I take that and I change that to a percentage by moving that decimal twice, I think I wrote that wrong. Okay. Then I get a growth rate of about 14.5%, right, rounding on this 4. And so what that tells me is that that the population of turtles is growing well, that actually works. It's growing by about 14.5% per year. So 2 different models, one for linear growth, one's for exponential. The last thing we need to do here, right, the last question, it says that in year 12, right, T equals 12, the biologist estimates there were 900 turtles. Right? And it says, what does that indicate about the 2 population models? So what does that tell me is better, the linear model or the exponential model? Well, we will test them both. A model is supposed to predict what will happen. So if we come back to C, we had the point 12, 900, right? This was time, this is my population of turtles. So if I go to my linear model, right, so my population based on my linear model at 12, right, should be should be 100 plus 50 times 12, right, which is 700. If I take this point and I plug it into my exponential model, then I plug 12 into the equation, which is 174.716 times 1.1447 to the 12. And I make that substitution and I get 884.500. So, which model was better? If the actual population was 900, then I come here and I compare these two predictions on how big that population will be, and we could see that the exponential prediction was closer to what actually happened than the linear was. So therefore, the exponential model, right, appears to be better. Because the predicted population was closer to what actually happened. Okay, I think we'll stop there, and I'm not going to do the last example on these notes at this point in time. So, all right, so you should have another couple problems you should do. All right, do a great job.